In our previous discussions, the topic was hypothesis testing, and just a general overview of the individual components of the test. That was a little confusing, as well as should be, because we didn't run through an entire test start to finish. So hopefully by the end of this video, things will be a lot more clear. Because one of the things I definitely want to do, I want to do some review of the individual components, but then I want to run through an entire hypothesis test start to finish. And so in this video, we're specifically looking at hypothesis testing on the population proportion. Now, we'll talk about the population mean later, and we could do hypothesis tests on all the different parameters, the variance, the standard deviation, and so on. But in this video, I'm going to focus on the proportion, and specifically one sample from one population. The discussion of two samples, that'll come later. All right, so basically what we're doing is we're starting off, so let me number this. We're starting off with a claim. And what I mean by a claim, it's a statistical statement that's declarative in nature, basically saying something. In the context of proportions, the claim is going to be some declarative sentence regarding percentages of something. You know, the claim might be 46% of registered voters in this district support this, amendment, whatever it is. And what we want to do, the testing that's involved here is determining whether or not the data, the available data, backs up the claim. Okay, so you're going to start with the claim, and that's going to be, for all intents and purposes in this class or in any stats class, the claim that's given to you in the problem. And what you want to do with the claim is represent it symbolically. So basically the claim is going to be either the proportion is equal to some number, the proportion is not equal to some number, the proportion is greater than or equal to some number, and C is just any number from 0 to 1. Remember, proportions deal with percentages, so the only available values are between 0% and 1 for 100%. So P is going to be between 0, C is going to be between 0 and 1. So proportion is strictly greater than some number, proportion is less than or equal to some number, and proportion is strictly less than some number. You don't necessarily have to take such detailed notes while watching this video, because I'm going to supply you with this document that I created, which is basically giving you the step-by-step instructions. And I'll go back and forth between my whiteboard and these instructions, but I'll email this out to the class. Okay, so going back to here. Okay, so we have these 6 options for the claim, and you're looking for keywords like in the problem itself. You're looking for words like more than, at least, at most, less than, is equal to, is not equal to, is. So some keyword that corresponds with one of these 6 quantifiers: equal, not equal to, greater than, and so on. Now, once you have that claim, the next thing you want to do is establish your 2 competing hypotheses. So you have the null hypothesis, and that's your default position. That's your assumption, unless the data is strong enough to reject that. And the null hypothesis, the symbol is H0, and there's only one option. The null hypothesis is always a statement of equality. So for the proportion, it's going to be the statement proportion is equal to some number. So that's going to be your null hypothesis. There's no options there. There's no choice. Your alternate hypothesis, though, the symbol we're using for that is H1. Well, there's 3 possibilities there. The alternate hypothesis cannot contain equality. So it can't be an equal sign. It can't be a greater than or equal to sign. It can't be a less than or equal to sign. So your alternate hypothesis is either going to be the statement proportion is not equal to this number C, the proportion is greater than this number C, or the proportion is less than this number C. Right? So those are the three options for the alternate hypothesis. And the alternate hypothesis is important for setting up the test, because this is telling you what type of test it is. So if your alternate hypothesis is not equal to, or basically if the problem doesn't include any wording that tells you more than or less than, if the problem is missing the more than or the less than language, it's going to be not equal to. And that's going to be a two-tailed test. And if the alternate hypothesis is greater than or less than, it's going to be a one-tailed test. So if it's greater than, we're looking at a right-tailed test. And if the alternate hypothesis uses the less than symbol, it's going to be a left-tailed test. Now, once you have your null and your alternate hypothesis set up, the next thing you want to do is identify all the important numbers and values associated with the problem. Identify all the important numbers. So, for example, we need to know the level of significance, which is alpha. That's going to be given in the problem. We need to know the sample size, n. That's also going to be given in the problem. And since the distribution of sample proportions could be approximated by a binomial distribution, we have to, well, one, we have to follow the requirements of the binomial distribution. So fixed sample size, independent samples, and we need n times p and n times q both to be larger than 5. So that's something we'll check, and I'll talk about that later. So we need the population proportion. We need the complement of the population proportion, q. We need the sample proportion, and the sample proportion is calculated by taking x, the number of successes, and dividing it by the sample size. Okay, and I have all this laid out in this Word document. So let me just go through these steps, what we have so far. So we talked about number 1, start with the claim, and we have these 6 options here. Set up the null and the alternate hypothesis. The symbol used in the alternate hypothesis determines whether you have a one-tailed test or a two-tailed test. And now we're talking about identifying the important values that we're going to use in our calculations. And now this one in particular, alpha, the level of significance, which is given in the problem, that's what we use to determine the critical value or values. Now those are z-scores, and it's the same critical values that we've been talking about for the last 2 chapters. This is the 3rd chapter that we're using these same critical values, and the Excel functions for determining those critical values. It's the same normal standard inverse function on Excel. So for this critical value here, where this red shaded area, that's alpha. We're using norm.s.inv, and then the alpha in the parentheses is the argument of the function. Or if it's a two-tailed test, half of alpha is on the left. We saw this in the previous chapter with confidence interval estimates. Half of alpha is on the right. So we have a negative critical value. We have a positive critical value. And so we have these 2 Excel functions for that. And if it's a right-tailed test, remember, Excel only works with area to the left. So if this area to the right here is given by alpha, well, this green area will be 1 minus alpha. So if alpha is 0.1, the area to the left would be 0.9. And that's why in this Excel function down here, we have a 1 minus alpha. So this critical value here, norm.s.inv, and then in parentheses 1 minus alpha. All right, so what we're basically doing when we're testing the hypothesis is we want to determine whether we should use the null hypothesis, or if the data is strong enough to sort of fall back on plan B, which is the alternate hypothesis. You think about this as a trial in court, a jury trial. So in this country, you are presumed to be innocent until proven guilty. So your null hypothesis, your default, your plan A, your null hypothesis would be innocent, unless there's enough data available to reject that, and then fall back on the alternate, which would be, oh, sorry, we don't say innocent, we say not guilty. Those are not exactly the same thing. So you are not guilty, and then if there's enough evidence to show that you actually did commit the crime, then your alternate hypothesis would be found guilty. All right, so this is what's going on with this alternate, this null, which is sort of plan A, versus alternate, which is plan B, hypotheses. You assume the null hypothesis is true unless there's enough data to reject that, and move on to the alternate hypothesis. And the way we do that is we take the data available and compare it to the critical value. And the critical value is associated with alpha, the level of significance. Right? So the next thing we're going to do is find the critical values. I'll say value or values. If it's a one-tail test, there's one critical value. There's a two-tail test, there's two critical values. This is using alpha and Excel. All right, and that's the same Excel functions. This is the third straight chapter we're using the same Excel functions. We're given the area, right? So alpha is given. And we use Excel to find the z-score. And that z-score or z-scores are the critical values. And then once we have the critical values, we find a second z-score. So we're going to compare these two z-scores and see which one is bigger. And we'll calculate the test statistic. Now what the test statistic is we have some sample data, and that's going to be our sample proportions. We take our sample data and we convert it to a z-score. And that's going to be our test statistic. And the way we do that is we use the formula z is equal to p hat minus p divided by the standard error of the proportion, which we talked about in chapter 6, which is the square root of p times q divided by n. All right, so we'll use that formula to calculate the z-score. So now we'll have two z-scores. We'll have the critical value z-score, and we'll have the test statistic z-score. And it turns out there's actually two methods. There's two methods to determine what we do with the null hypothesis. Remember, this whole process is determining, let me scroll up here. This whole process is determining what to do. What do we do with that? What do we do with the null hypothesis? Do we keep it or do we reject it? It's keep or reject. And this whole process is determining whether or not we keep the null hypothesis or we reject it. Now to do that, we have two methods. One is comparing these two z-scores. The second one is comparing the areas outside of these z-scores. one of those areas is given, it's alpha, the significance, and the other area is called a p-value. Find the p-value. Now the p-value, or probability value, is the likelihood or the probability of making a type 1 error, rejecting the null hypothesis when you're not supposed to. So this p-value, it's associated with the test statistic. So you have to find the test statistic first. You need that z-score. And then you find the p-value. And the p-value, well, it depends on if we have a left tail test. So if the test statistic is here, that's the z-score, then this area outside of the test statistic, that's going to be the p-value. So in step 5, we figure out the test statistic, and then we find the area outside of the test statistic. And also, if it's a right tail test, same thing. Right tail test, we find this z-score, which is the test statistic. The area outside of that will be the p-value. Now, if it's a two-tail test, and remember, this is based on what the alternate hypothesis is. If it's a two-tail test, then the test statistic is either going to be positive or negative. It's not both. There's only one test statistic. So if it's on the right, we look at the area on the right. If it's on the left, we look at the area on the left. So let's say the test statistic is right here. We could find the area, again, outside of that z-score. And then the p-value is twice this area. So you double it. So if it's a one-tail test, the p-value is the area. So equals area equals area. And if it's a two-tail test, you double the area outside of the test statistic. Now, once you have the p-value, well, now you could perform two different methods. So we have two methods for, so the next step, so I'll say step 7, is determine what to do with the null hypothesis. So determine whether or not to reject the null hypothesis. Okay? And we have two methods for doing this. Both methods always work. Both methods take the same amount of work. There's never a case where you have to use one or the other. So the two methods are the traditional method. And in the traditional method, you're comparing, we'll say you compare two z-scores. And in that method, we'll say, 1, if the test statistic is further from 0 than the critical value. Right? If the test statistic, so let's look at a graph. Let's say, for example, you found two z-scores. And let's say the critical value is right there. So remember, the center of the graph is 0. Let's say the critical value is this z-score, and the test statistic is over here. Test statistic. In that case, you would reject the null hypothesis. Reject the null hypothesis. And if the critical value is further from 0, you fail to reject the null hypothesis. The other method is called the p-value method. So we have traditional method, p-value method. With the p-value method, you're comparing two areas. Let me make the test statistic a different color. I'm going to make it blue. Let's see. Test statistic is over there. Okay, so with the p-value method, if the p-value, remember that's an area, is smaller than the level of significance of the test, which is alpha, that's given in the problem. If the p-value is smaller, reject the null hypothesis. Now let's look at this. I'm going to redraw the exact same graph. I'm going to put the critical value and the test statistic in the same place. Here's the center of the graph. That's 0. Here's the critical value. And over here, let's put the test statistic right here. Okay, now the areas, well, the area outside the critical value, that red area, that's alpha. That's the significance. And the area outside the test statistic, that's this blue area, that's the p-value. So if the test statistic is farther away than the critical value, well, the area is going to be smaller. So in that case, we also reject the null hypothesis. Okay? And if the p-value is bigger than alpha, we fail to reject. All right, so this is two methods of doing the same thing. It's either, if you know area, you could find a z-score, right? And if you know z-score, you could find an area. So it's not like you'll ever have information for only one of these two methods. It's just basically two different ways of saying the same thing. You could go to the store, you could buy something with a $1 bill, you could buy something with 4 quarters. It's just two different ways of doing the exact same thing. All right, and that's it. Now, once you know whether or not to reject the null hypothesis, you are able to finish it up by stating the final conclusion. So step 8, state final conclusion. And there's going to be 3 options for the final conclusion. Either your data supports the claim, so the data backs up the original claim, or the data contradicts the original claim, so you reject the original claim. Or finally, the test could be inconclusive. And if the test is inconclusive, that just means you need more data. You need a larger sample. So let me talk about p-values and final conclusions real quick. Let me go over to my other document. Okay, so we've talked about the original claim, the null and alternate hypotheses, the values, the numbers relative to our calculations. We talked about one-tail, two-tail tests and the critical values associated. We talked about the test statistic using this formula right here. Now, in terms of finding the p-value, just follow this flow chart. So is it a left tail test, in which case the alternate hypothesis would be p is less than some number c. You say the p-value is the area to the left or outside of the test statistic. Or do you have a right tail test, which happens when the alternate hypothesis uses a greater than symbol? in which case the area again would be, or the p-value again would be the area outside the test statistic. Or do you have a two-tailed test, which happens when the alternate hypothesis uses a not equal to symbol. And in that case, whether it's left or right, doesn't matter. It's twice the area outside of the test statistic. So down here, sort of visually where the p-value is coming from. And then once you apply either the traditional method or the p-value method, remember with the traditional method, you're compare two z-scores. With the p-value method, you're comparing two areas. Compare two areas. Either way, the traditional method and the p-value method, they both tell you what to do with the null hypothesis. Just option A, option B. You keep the null hypothesis or you reject the null hypothesis. And once you determine that, the very last step, like I was discussing earlier, is to state the final conclusion. And you could use this flow chart for that. So there's two questions. The first question is, does the original claim contain an equal sign? So is the original claim P equals C, P is greater than or equal to C, or P is less than or equal to C? Right, in that case, you say yes, and you move on here. And then the second question, do you reject the null hypothesis, yes or no? So you're either here or here. So if the original claim contains equality and you reject the null hypothesis, you're at this box right here, you reject the original claim. Or if the original claim contains equality and you fail to reject the null hypothesis, anytime you fail to reject the null hypothesis, that means the test is inconclusive. And going back, does the original claim contain equality? If the answer is no, so if the original claim is not equal to, the original claim is greater than, or if the original claim is less than, you go down here. And then again, the question is, do you reject the null hypothesis? Yes or no? So if the original claim does not contain equality and you do reject the null hypothesis, that is the case where the data supports the initial or the original claim. And if you reject the null hypothesis, we say the test is inconclusive. All right, so most of this we covered in our last discussion. So what I want to do now is put it all together, and we're almost done. I want to put it all together and just go through a hypothesis test start to finish. And actually I want to get rid of that because that's the stuff we want to calculate. Okay, so you're looking at the original problem. Suppose 248 subjects are treated with a drug. That drug is used to treat pain. 53 of them developed a side effect, nausea. Okay, so 53 out of 248. Use a 0.01 significance level to test the claim that more than 20% of users developed nausea. Okay, so I'm seeing four numbers there. First, suppose 248 subjects are treated with a drug. That's our sample size. So over here next to n, I'm going to type in 248. Okay, 53 of them developed nausea. So that is the number of observations. So x is 53. Use a 0.01 significance level. Remember, significance level is alpha. So over here next to alpha, I'm going to put 0.01. 0.01. To test the claim that more than 20% of users develop nausea. So let me just say the claim that more than 20% of users develop nausea. So our original claim is more than. So we'll say P is greater than 0.20. Okay, now our null and alternate hypotheses. Remember, null hypothesis is you don't have to think about it. There aren't options there. The null hypothesis is a statement that contains an equal sign. So the null hypothesis would be P is equal to 0.20. And the alternate would then be that P is greater than 0.20. All right, so that's a right tail test. And I have this visual here. This graph is not going to be given to you in the problem, but I put it into this Excel file so I could use it during this video. I didn't have to draw it myself. Okay, so it's a right tail test. Now, so this red area over here, that's alpha. That area is 0.01. Which means this green area is 0.99. Okay, so now our sample data, P hat, that's the P with the little triangle, that's equal to X divided by N. Okay, so P hat, I'm going to just use the locations here. So let's say that's equal to the X. I'm going to just click on the 53. Divided by the N, I'm going to click on the 248. So B8 divided by B9. X divided by N. So that is our sample proportion. Okay, so we see that population proportion we're assuming is equal to 0.2. The sample proportion is a little higher than that, 0.21, 0.2137, something. Okay, so I'll go down here for P, that's the 0.20. And Q, well, Q is the complement of P, so Q is 1 minus P. So let's say equal 1 minus, click on the P, so 1 minus P. Okay, so now we have P, we have Q, we have P hat. Now remember, the test statistic, this guy right here, well, we're using the formula P hat minus P divided by the square root of P times Q divided by N. So the P, the Q, the N, and the P hat. We have those four numbers already. Right? We have the P, the Q, the N, and the P hat. So these four values are going in for the Z. And I'm actually going to use parentheses when I type it into Excel. So I make sure Excel is following order of operations. So I'm just going to type this formula in to Excel under test statistic next to test statistic. So let's say equal parentheses P hat minus P. So P hat, I'm going to click on P hat, that's B10, minus P, which is B11. Close the parentheses. Divided by the square root of, so XQRT parenthesis, that's square root of, P times Q divided by N. So I'll click on the P, multiplication sign by the Q, division sign, divide by, then I'll click on the N and I'll close the parentheses. So if you want, just take a moment, pause the video, just make sure you're clear on typing that formula into Excel. Okay, so there is our test statistic. So now we need the critical value. And the critical value is coming from alpha. The critical value is this z-score down here. I'll say CV for critical value. That's the z-score. And that's the z-score with 0.01 of the area to the right or 0.99 of the area to the left. So I'm going to use equal norm.s.inv 0.99 or 1 minus alpha. Okay, so equal norm.s.inv parentheses. Now you could type in 0.99 or I'm just going to use 1 minus alpha, which is right here. I'll click on that. 1 minus alpha. Okay, so there's our critical value, 2.32. Okay, so now let's look at the graph. This critical value is the z-score 2.33. And the test statistic is over here. That's the 0.54. I'll round to 2 decimal places. Okay, so the test statistic is smaller than the critical value. Okay, the test statistic is smaller than the critical value. So according to the traditional method, okay, the test statistic is less than the critical value, so we fail to reject the null hypothesis. Or we could use the p-value method. Now remember, the p-value is this area outside of the test statistic, that green area that I just shaded. And so the p-value, well, Excel can't give us directly the area to the right, only area to the left. So we use, again, the complement rule, which is the same exact one we used back in chapter 6. So the p-value will be equal to 1 minus the area to the right. And so we're using 1 minus norm.s.dist. The z-score is the test statistic. That's the 0.54 or 539,751. And we always use yes or 1 for the cumulative function. It's the same thing we've been doing for chapters 6 and 7, now in chapter 8. Okay, so the p-value method in this case, which is the 0.29, is greater than the significance, which is 0.01. So again, that tells us the same thing. Fail to reject the null hypothesis. So whether we're using the traditional method with the 2 z-scores or the p-value method with the 2 areas, we come to the same conclusion. Fail to reject the null hypothesis. So, original claim. The original claim contains a greater than sign, not an equal to sign, just a greater than. So if I go down here, I have that same flow chart over here. So, does the original claim contain equality? No. The original claim was P is greater than 0.2. And let's make this a little smaller. Do you reject the null hypothesis, yes or no? No, we failed to reject the null hypothesis. So that puts us down here. So our final conclusion is inconclusive test. There is not sufficient evidence to support the claim. There is not sufficient sample evidence to support the claim. And that's the last step in this hypothesis test. All right, so let me go back to the original problem. Test the claim that more than 20% of users develop nausea. Maybe they do, maybe they don't. This is not enough data to support that claim. All right, we're not rejecting the claim. We're just saying we don't have enough data. We need more data to determine whether or not we can support that claim. Okay, so where we end up in these four boxes here on the right, where we end up, it doesn't mean the problem is done the same way. Critical values, test statistic, p-values. What do I do with the null hypothesis? And once you've answered those questions, then you come down to this flow chart to determine the wording of your final conclusion. Okay, so that does it for this. So like I said, you want to really keep handy this document that you should, by the time you're watching this, you'll already have this document. And this is just your algorithm, your step-by-step process for testing a claim about the proportion. Now, this is just for the proportion, but the steps for testing a claim about the mean are going to be pretty much identical. Same steps. See, the exact same steps. Same 8 steps. The only difference is right here in step 5. When we switch to the mean, we're going to have a different formula for the test statistic. But other than that, section 8.2, which is the proportion, and section 8.3, which is the mean, those problems, the same 8 steps are what we use for problems from both sections. The only difference will be step 5. We'll have a different z-score formula. All right, that about does it for this video. The next discussion will be hypothesis testing on the mean.